We'll start with how the cells in an adaptive product are allocated. In this example, we can see that the distance between the array and audience surfaces changes drastically between the closest points and furthest points. At the closest point, the array is just 25 feet from the nearest audience surface, though at the back of the venue, the array is nearly 150 feet away. So how do adaptive products address this extreme difference in distance? The inverse square law tells us every time we double the distance from our sound source, we're going to lose about 6 dB. To compensate for this loss, the adaptive algorithm will weigh the audience areas and assign the appropriate number of cells. This means that if we compare our furthest point to our closest point, the furthest points will utilize the majority of the components in the array, with the closer areas utilizing only a small percentage. It's important to note that this type of allocation is not possible with the traditional line array. In this example, we're able to take hundreds of components and direct them at the furthest points in the venue to achieve a constant result, all through software. To do this physically with a traditional line array would not be possible given the physical constraints of the boxes themselves. The result is nearly perfect coverage across all seating. Here's another example. In this case, the venue is nearly twice the length, which is a much steeper vertical incline. Utilizing the same allocation techniques from our previous example, we see the coverage is perfectly consistent to nearly 300 feet out. The adaptive algorithm process also involves EQ optimization. Because we know all our variables ahead of time, adaptive systems can perform a self-optimization EQ process, perfectly matching the system response with the desired target response. So how does it work? To measure the predicted system response, Resolution will place virtual microphones within the venue and develop an average system response that it uses as a baseline. This process is invisible to the user. The microphones represented here are only shown to demonstrate what is happening behind the scenes. Once a baseline response has been established, it's time to analyze and adjust to our target voicings. Let's say, for example, the pink trace above represents the measured response from our model, and our desired system response, or target voicing, is shown as the red trace. You'll notice there's a buildup of energy centered at 150 Hz. This is a common occurrence if you have a multi-column array of Anya or Anna. Low frequency energy will sum constructively between the two columns, resulting in a buildup of energy in this range. Because we can model and predict this behavior, we can also correct for it automatically. In this case, Resolution will compare the measured response to the target response, calculate, and then implement the optimal filter needed to match the measured response to the target. The result is a system that is show-ready and essentially pre-tuned, substantially reducing the system optimization time. Also taking place is high-frequency air loss. Significant attenuation to high frequency of a sound system occurs when that system is used over extreme distances. We call this effect air loss. To combat this and provide the best possible high-frequency response for a given condition, EAW employs an automatic air loss compensation algorithm in its adaptive products. Air loss is linear with distance, meaning that as distance increases, so will air loss at a linear rate. To demonstrate the effects of air loss, let's look at a basic example. This image shows the effects of air loss at different distances. We've also normalized the response to 1 meter. This allows us to compare the effects of the high-frequency attenuation introduced by air loss more clearly. You'll notice that the effects of air loss close to the sound source at 50 and 100 feet are quite subtle, though as distance increases, the effects become quite dramatic and have a significant impact on the tonal balance of a sound system. Here we can see the result of applying air loss pre-emphasis. The red trace is representation of the air loss we encountered at 400 feet from the source. The brown trace shows the boost of pre-emphasis that will be applied, and the orange trace is the result of applying that boost to the red trace. Lastly, we have Spatial EQ, one of our newest features. This lets users simply select a part of the audience they want to EQ and make the change in real time. The system figures out what part of the array it needs to affect and makes the changes for them. It is, for the first time, actually EQing the room. This speaks to adaptive as a platform, one that can upgrade over time. This is not possible with other loudspeakers. Now that we've had a look at what happens with a single column, let's expand on that and look at what happens when we add multiple columns and array them horizontally. Let's take a look at a larger venue in a situation where two arrays are different lengths. Here's the multi-column array that we will be working with. The longer line length will be assigned to the longer throw, and the shorter line length to the shorter throw. Now that we have a multi-column array containing two different sized columns aimed at different audience geometry, Resolution will need to make a decision on how to best align these two columns. The most logical point to align the two arrays is at the point where the majority of the audience is seated. This ensures the best possible performance to the greatest number of audience members. Resolution does this by analyzing the audience area covered by each array, identifying the cross-section that contains the greatest audience area, and aligns at that point. In this example, the blue area represents the coverage of the main Anya column, 12 modules, and the green area represents the coverage of the shorter side Anya column, which is 8 modules. The alignment will occur at the position indicated by the highlighted oval. This is the optimal alignment point for this venue and ensures the best performance over the largest possible audience area. Using IR sensors, each cabinet knows its relative position in the array. Each array is processed and controlled as a single unit, not individual modules. This eliminates the possibility of user error in array assignment or inappropriate processing that will negatively impact performance. Adaptive modules are always self-monitoring. If a fault is detected, it will notify the user by a red indicator on the back of the amp or in the resolution software. It's possible to heal around this fault and recalculate. This will reassign all cells excluding the faulty ones in the same coverage area. Adaptive Systems also gives access to a series of diagnostic logs. This way it's possible to monitor and investigate temperature, errors, and impedance. Dante provides seamless audio backup through primary and secondary networks. In the event that the primary network connection is interrupted, the system will automatically and immediately switch to the secondary without any pause in audio or control. Using a star topology for Dante and control, along with onboard amplification and DSP, ensures that significant system failure is not a possibility. In a traditional array, the loss of an amplifier channel will eliminate several cabinets or passbands from the array. As we've mentioned prior, Adaptive is a platform. The addition of new features should prove this as we continue to upgrade and to add new functionality. Unlike other systems, these upgrades can improve system performance with just a download. A great example of this is something we added most recently, Spatial EQ.